This is video 32 in the series on concrete slabs, but this video will deal with columns and it will show you how to deal with buckling calculation. A column is always designed for combined bending M and N. M is the total bending moment, first and second order, and N is the load, vertical load, compression load, or tension load on the column. The eccentricity is M over N. N, of course, is the NED, and M is the first order plus the second order bending moment. The total eccentricity is the first order eccentricity plus the second order eccentricity, and it means that the total bending moment is NED times E1 plus NED times E2. Very simple up till now. E1, the first order eccentricity, is E0 plus an accidental eccentricity. And the accidental eccentricity is the effective length of the column divided by 400, effective length in millimeters. And E0 is the maximum of 20 millimeters. The cross section, the cross section, the dimension of the cross section of the column divided by 30, but it's the dimension of the cross section in the same direction of the acting bending moment M. And then E0 is, of course, the maximum also of the external applied bending moment divided by the normal force, external applied bending moment. That's the bending moment coming from the loads. And E2 is the second order displacement. Now, all of that is known except the second order displacements we do not have. So how can we calculate this? Let's take the model column. This is the elastic line. This is a virtual elastic line, and this is where we will put our XY axis. The total buckling length is L0. It's 2 times L. It's loaded with a bending moment and a normal force, and the eccentricity of second order is E2 because this is eccentrically placed. The equation of the eccentric line, we have seen that it is A equals, in our reference axis, it's minus C sinus AX. And A and C we will find by the conditions at the beginning. When X and Y is 0, then it is okay. Then this is fulfilled. But when X is equal to L0, this point on top, then Y here, because Y is here, then Y, here at this point, then Y is 0. So that means that that means that alpha L0 must be equal to pi, or A, not alpha, A is pi over L0. For the midsection here, when X is equal to L0 over 2, then we see that Y is equal to E2, but minus E2. And then you can see here that the value C must be equal to E2 to fulfill this condition. So A is P over pi over L0 and C is equal to E2. We can write that in our elastic line equation, and we have obtained this form. We take the first derivative and then the second derivative, and we know that the second derivative is equal to the curvature, 1 over rho. And when X is equal to L0 over 2, then we see that the curvature is equal to this, or E2 is equal to L0 squared divided by pi squared times the curvature, 1 over rho. Now we have an expression for the second order displacement. At maximum capacity, then we know that the NED is equal to NRD, for R from resistance is equal to N, and MED equals to MRD is M. M is M1 plus M2, that we have seen already. We now know that the eccentricity of second order is given by this equation. And this, when you look carefully at it, you can put it in a graph with the curvature on the x-axis, the bending moment m on the y-axis, and you will see m1, that is the portion on the y-axis. And for a certain value of the normal force, and d is for instance equal to n1, then you see that this portion is the tangents of this angle, and it's equal to this portion here. So it's a graph m in function of the curvature 1 over r, and it's a straight line. This is the relation between curvature and bending moment, but this is only taken into account the geometrical conditions. There is no reinforcement in this equation. That's not there. So it's external. It's an external stability independently from reinforcement and tension or stresses. But we know that each section needs to have a resistance against N and M internally. So the bending moment is a function of strain in the steel and strain in the concrete. The normal force is also a function of strain in steel and strain in the concrete. But at a certain normal force, N1, you can now also make a graph, M in function of the curvature. And this graph make a form like that until it breaks down, and this for a certain value n equals to n1. The curvature r is equal to rho. The curvature equals, like we have seen, the strain divided by the distance to the neutral axis, but here we have taken the total strain, so we have to take d. It means now that the internal stability, it depends, of course, on the reinforcement and the stress. We can draw different curves for the internal stability, and doing so you will see that those curves break off at a certain point, and here at this point it's the steel which is not fulfilling its task anymore. So the steel is the cause of the breaking down of the bearing capacity. Other lines break down here, and then it's the concrete which is crushed. But before the concrete is crushed, you have another line which indicates when the first cracks appear. So you have different equations for M and the curvature, and you have the different situations, or the steel or the concrete is the cause, and this is where the concrete is cracked. Now we have the bending moment versus the curvature, but we have two curves. And where those two curves have an intersection, that means there is an equilibrium. And such an equilibrium is stable when, with a small increase in curvature, the eccentricity of the internal stresses rises faster than that of the external forces. So the resistance gets a little bit bigger than the acting forces or acting stresses. When those 2 points comes together, then you have a critical normal force. So this is the external equilibrium. This is the slenderness has to do with it, and this is internal. This is concrete grade and reinforcement, and it's only 1 point when there is an equilibrium. We take, for instance, an internal curve N2 with the external curve with N equals N2. And when you have a situation like that, those two touches here in this point of this intersection point, then we know that there is a collapse of material. It's not the slenderness that is important, that is making the column collapse, but it's internal. It's the material, in fact, the material that collapses. that the column is collapsed. When you have a situation like this for N2, then this is a collapse by internal stability, the geometrical instability. So it will be the slenderness that is not enough. And a third, okay. Then we can look when the bending moment is 0, then everything comes in the point 0, 0. Then you will see that N1, when for N equals to N1, this point is a stable equilibrium and the column will hold, and there is no curvature at all of the column. So the column stays straight. In this case, when this is just tangent to the point O to this curve, this is unstable. It's a very critical load N2, and in the slightest movement on the top of the column will collapse. And in the case where this line is steeper than the tangent to the line, then there is no equilibrium possible. Each load will lead to failure. Now let's go to Eurocode 2 part 1.1, and there they have a calculation method of nominal curvature for the calculation of slender columns. And they defined a bending moment, a first order bending moment, as 0.6 times MO2 plus 0.4 times MO1, and it must always be bigger than 0.41 MO2. And the definition is MO2 is the bending moment on top and on bottom, but the absolute value of the bending moment MO2 is bigger than the one of MO1. So you can have this case, for instance, or you can have this case. And M2 is, of course, the second order bending moment. It's the normal force times the eccentricity E2. And MED, the total bending moment on the column, is the first order bending moment, this one, plus the second order bending moment, just like seen in the previous slide. The method of nominal curvature leads to a second order moment equals to N times E2. N is the design value of normal force. E2 is a second order deflection. It's defined L0 squared divided by a coefficient C multiplied by the curvature. C is 10. It is in fact P squared. The effective length L0, and the curvature is given by KR Kφ times 1 over rho 0. It's those coefficients Kr and Kφ, they take into account the shrinkage effect and the moment distribution. 1 over R0, again, it is a strain divided by a distance to the neutral axis. So it is here defined by the strain in the steel divided by 0.45 times the effective depth of the cross section. And epsilon yd is of course equal to the yield stress divided by the modulus of elasticity of the steel. Kφ, like I said, is a function of the creep coefficient. Beta, again, is defined or is depending on the slenderness of the column and on the concrete quality. And the slenderness of the column is L0 divided by the radius of gyration. But like we said in the beginning, that we know what this is. And Kr, it's a coefficient that gives the moment distribution alongside the length of the column. N is the load rate, and N ball is of Nu. Nu is equal to 1 plus omega, and omega is the mechanical reinforcement ratio. And N ball is 0.4. For more detailed calculations, N ball can be calculated more precise. But for most cases, this will be sufficient. Then we have the second method is the moment magnification factor method. Then the second order bending moment. We remember we've seen that in the previous slides that you can say that the bending moment of the second order is the normal force times x, the displacement. And we've seen that x is equal to NED divided by N critical minus NED times E1. And M2 is equal then, when we substitute to this form, and you can rewrite this form like we've seen in video 30, we can rewrite it and then it will have this expression. And M1 is ND times E1. And M2 is M1 divided by this. And then we will see that M equals to M1 plus M2, and we can rewrite it in this form. Now, just to tie in the slides with the Eurocode 2, we then see that M is equal to MDEDM, M1 is MOE, and N critical is NB, of N ball, and NED is NRD. And beta M is a distribution of first and second order bending moments and can be put equal to pi squared over 8. And NB is equal to the force of Euler. The nominal stiffness is estimated by ECM YC, because this is not an exact calculation, does not take into account the reinforcement, but this can be sufficient. So if you now make all those substitutions into this equation, then you will have the equation as it is mentioned in Eurocode 2 part 1.1. So these are two methods of calculating the columns subjected to buckling. There is also a minimum reinforcement, and the minimum size of reinforcement that you use in any column is diameter 12. And the minimum value of the reinforcement is 10% of the normal force divided by the yield stress of the steel, and must always be bigger than 0.2% of the cross section. The maximum reinforcement is of course 4% of the cross section. And at least one bar must be put in every corner of the cross section.